At the beginning of a typical course in calculus of several variables, there's a unit on vectors, lines, and planes to serve as an introduction for thinking and visualizing in 3D. Maple's Student MultivariateCalculus Calculus package contains functionalities for working with lines and planes, and you can either use a set of 16 commands or go syntax-free with the context panel. So this webinar gives an overview of these tools, illustrates them by a set of examples that you would find in the typical course or textbook. There are two constructors, one for a line and one for a plane. So these are commands, line and plane, they're commands. They construct a line object or a plane object. And I think they end up as a module in Maple, and I think of a module as a basket into which you put the properties and all the details of this object, and then you can rummage in the basket and pull out stuff as you need it. Okay, so to interpret these two commands and their effects, let's make the notation clear. Points are lists. I use Roman. Vectors are bold. Roman. This is italic. This is Roman. Wedge brackets are just inequality symbols, or you can use the palette, the matrix palette, to make a vector. Line object, I will have a symbol with a bar over it. Plane object, symbol with a bar over it. Now, just as a line would be determined mathematically, the same things would determine line here in the package. So linear equation or linear expression, 2D, in 2 or 3D, 2 points, in 2 or 3D, point and a direction vector. Parametrically, in 2 or 3D. In 3D, 2 planes intersect. They form a line. In 3D, a point and a plane. Well, the direction of the line would be the direction of the normal to the plane. And then also, the line command can be applied to an existing line object if you want to change its properties. Similarly, for the plane, you have a linear expression, a linear equation, or a linear expression. 3 points, a point, and a normal vector. I've just taken the bold off this A because it's really just a point. Okay, so 2 points and a direction. So the plane will contain those 2 points and that direction vector. 2 vectors and a point. So the plane contains that point and both directions. You clearly get the normal to the plane from the cross product. A line and a point not on the line. 2 lines. Now, if the lines are skew, the plane will contain the first line, but will be parallel to the second line. And if the lines are not skew, then the plane will contain both lines. Point and a plane. Clearly the plane will contain the point, and it will be parallel to the plane P. And again, if it's already a plane object, you can apply the command to it so that you change its properties if you want to. So let's take a quick look at the 16 commands in the package. These get commands will return you properties. Dimension, are you in 2 or 3D? Direction, vector, an intersection, a normal vector. Here you will get a graph. This is the only command that is not available through the context panel. You can get a point on it on a line or a plane. Get representation gives you the equation of the line or plane. This is a query. Do these objects intersect? Does this object contain that object? What is the distance between these two objects? Are these two objects equal? This is for lines. Are they planes? Are they parallel? Lines, are they skew? Are these two objects orthogonal? What is the angle between these two? And this is orthogonal projection of a point to a line, point to a plane, line to whatever. Now, when you get the representation of a line, you have some choices about how it's going to be displayed. If you say form equals equation, you get an equation. If you say equations, you get the equation in set braces. If you say vectors, you will get this vector notation unmultiplied out. Parametric is obvious, symmetric is obvious. If you say combined vector, then this vector form is combined and you get what's essentially parametric without the equation x equals y equals. In 3D, there is no equation form, but you can get an equations form for these two equations. But then vectors, parametric, symmetric, and combined vector is the same. If you ask for the equation of the plane, that's exactly what you get. If you put an S on it, it comes back as a set. And that's the only way you can represent the plane. With respect to syntax-free computing, let's make an observation here about the use of the context panel. The arguments are put into the worksheet. Context panel then gives access to 15 of the 16 commands. There are a couple of places where you have to make sure that Maple is looking at the contents of the object, not just the name of the object. You'll see that in the examples that we're going to do next. Example 1. Obtain an equation for the line through a given point with a given direction. Fairly straightforward. Let's see how a syntax-free solution shapes up. Okay, I've got a lot of stuff typed in, so we're not spending a lot of time watching me type. So I'm going to just re-execute these things so that I can show you where they come from. First, I loaded the Student Multivariate Calculus package. I'll do that only once here for you. Tools, load package, Student Multivariate Calculus. Okay, so that loads the package. The fixed point is given as a list, so square brackets, comma. The vector, wedge brackets, which are inequality symbols. Click on that. Go here to the context panel, Student Multivariate Calculus, lines and planes. Pick line. Okay, when you pick line, this pop-up will appear, and you set the variables. The defaults are X, Y, Z. I keep them. Then when the line object is created, and this is what the line object is displayed as, you can query it for different things. And if you query it for representation, you will get this pop-up. Now, the parameter t is the default. You can change that. I have selected combined vector. This is what the combined vector looks like. Except for the x equals y equals z equals, it looks like parametric form. Solving this problem with the set of commands. Okay, so here are the commands. Line command, you give it the arguments, point, vector, and this is the assignment operator assigned to L1, and you'll notice that here, since we're working with commands, I've loaded the Student Multivariate Calculus package with the with command. Okay, so I hit the enter key, get back a line object. You can use the get representation command to get the equation. So you must indicate form equals. So here I've said combined vector. If you say parametric, then you get parametric equations. If you say symmetric, you get the symmetric form of the line. And if you say vectors, you get the vector form, but the multiplication and addition has not been carried out. The traditional vector solution would look like this. The point P is given as a position vector, so it's defined P equals. And here we use the context panel to assign name. So this becomes an assignment, even though we've used equal. This is the direction vector, same thing. This is the generic position vector. And then the form of the line is P plus TV. Hit the enter key, and you get XYZ equals 2 plus T, etc. Example 2, equation of a line through two given points. So the syntax-free solution will look like this. Same structure as in the first example. Load the package. Now you put the 2 points as 2 lists. Then everything else is the same. Make the line. The line object is displayed here. You then ask for the representation. You get these 2 pop-ups. Choose the variables. X, Y, Z are defaults. And here I have picked combined vector. Solve that problem using commands. You would load the package using with. You apply the line command. Here are the 2 points and the assignment operator, giving it the name, assigning it the name L1. Get representation. You must know the syntax here. Form equals. Combined vector gives that. Parametric gives that. Symmetric gives that. And vectors gives this. The traditional vector approach could be implemented as follows. The fixed points P and Q are given as vectors, again using the assign to a name operator here. Assign name, right? Because the name is already given here. Generic position vector. And then to get the direction, do the subtraction in place. Q minus P gives you direction from P to Q. P plus T times that vector, you get this form of the solution. Third example is a bit more complicated. You have 2 lines, A plus TP, B plus SQ, and the AB, BQ, or PQ can be extracted from these 2 equations for the lines, parametric form of the lines. Well, you want to show that they neither intersect nor are parallel, and hence are skew lines. And then you want to find the common normal between these 2 skew lines, or the planes containing the skew lines, and then find the distance between the 2 lines. Let's get to a page where we can work on this problem. Syntax-free solution. Okay, again, things are typed in to save time, but I will execute many of these so that we can see how they work. Okay, so I've loaded the package. You've seen that done before. The lines are given parametrically, so you put those 3 equations in a list, and then you do the obvious. You go to Student MultivariateCalculus, lines and planes, pick line. And then when you get the line object, do assign to a name. So L1 here, L2 here. Now we want to check on the skewness. So we type L1, L2. So again, let me execute that. We type L1, L2. These are the names. Now, if you simply click on the names, you don't get access to the properties. You have to do the evaluate and display in line, which is this item here. And that's a keyboard item. Two different ways. I always use Control Equal. There's an alternate way. It's Alt Enter. But my fingers are trained to do Control Equal. So in order to be unambiguous, evaluate and display in line. When you do that, then Maple is looking at the line objects, and now when you go to lines and planes, you have these queries. Down here it says skew. So that's what I selected, and Maple comes back and says true. These are skew lines. The other queries, and I'll do that here, the other queries are parallel. And I'll show you here, lines and planes, parallel. You click that, Maple says false, they're not parallel. And similarly down here you ask intersect, Maple says no, they don't intersect. Common normal. So here are the names, L1, L2. And notice that here, lines and planes, you can create the plane. So I think, in fact, I will just re-execute that. Create the plane. When you get the plane object created, you can go to Student MultivariateCalculus, and now you have these things that you can look for, and you pick normal, and there's the normal, a common normal, to the two parallel planes that the skew lines will reside in. Now, from the textbook vector approach to this, you could get the direction vectors for the two lines and take their cross product. So here I'm taking the two lines, and again I'll execute that so you can see. If you click on L1, you don't even get Student Multivariate Calculus. You've got to do an evaluate and display in line. Then Maple sees the object, and it lets you select the direction, and you get this vector, which is the direction vector on that line, and I've assigned it the name V1. Similarly, I did the same thing here for the other line. I just re-execute that. So now you have the two vectors, and you can do a cross product of the two vectors. And let me just show you a little bit about that cross product. So here's my stack of palettes. In my palette, I'll go here. In my palette, I have a favorites palette, and there is a cross product symbol. Now, how did I populate my favorites palette? Well, I found things that I use a lot, like this cross product symbol, and here's a dot, and here's a del. Okay, so you right click on the symbol you want to move to your favorites palette, and it says add to favorites. So I've populated my favorites palette. Here's how I got the dot product. So take the not the dot product, the cross product of these two vectors, and I get the same vector that may be provided up here. To find the distance, let's execute this line so you can see the pieces. If I click on the two names and I go here, Maple does not know what I want to do with these because it just sees two names. So you do an evaluate and display in line. You get now the line object displayed, and now Maple says, oh, here are things that you can do, and you say give me the distance, and I have this number here for the distance, the exact distance, 16 over the square root of 11. Notice how Maple automatically rationalizes that denominator. And then if we go here to approximate, you can pick the number of digits you want to approximate that number to. Command-based solution would run something like this. Again, with the package, define the two lines using the line command. Here's the assignment operator, square brackets around the parametric equations. You get these line objects. You can use the command rskew are parallel, intersects. Applied to the sequence L1, L2, you get true, false, false. Create the plane that you can obtain for L1 and L2. Remember, these are skew lines, so the plane will contain L1, but it will be parallel to L2. And you can wrap the get normal command around that, so all you see is the normal. Or you could get the direction for each line and take the cross product of the resulting vectors that you get, and you get the same thing. And then you can apply the distance command to L1, L2, and you get the same thing, 16 over the square root of 11. And if you float it, you get the same number that you would expect from above. So also, here, since you're using commands, we can investigate this get plot command. So, get plot, we apply it to L1. I hit something here. You can apply it to L2. You can apply it to each plane, which you obtain by applying the get point to L1 and get point to L2. So you have a point and a normal. So you can get plane, then you get the get plot applied to that, and then you put it all together with a plots display. And so here's what the resulting figure is. One plane, the other plane, they're parallel planes. One line is in this plane. One line is in this plane. Okay, so you can easily draw that picture with the get plot command. The traditional vector approach requires a lot more work. And here I've broken the three parts separately. First thing is, here's a picture of the parallel planes, the skew lines, and the common normal. It's great to start with a picture that shows you what you're trying to get at. Now, the way you would work this is you take two equations, x of t equals x of s. So you set the x coordinates equal of the two lines and the y coordinates, and you solve for the st pair for which these two lines have the same x and y coordinates. It's like standing on the ground looking up at two contrails from airliners that have crossed, and you're looking up and you say, what is the point directly under where these two contrails cross? So you get an S and a T, and then you go to the Z coordinate of each line and you evaluate at the value of T and at the value of S. So you get the two heights. You get the height on the one line and the height on the other line. If those two heights are different, then the lines lie one above the other, and they'll be skew lines. If these two numbers were equal, then the lines would intersect. This is the direction vector for the first line. This is the direction vector for the second line. To get the common normal, you take their cross product. Part B, the common normal. We already found it. It's right here. Part C, the distance between the lines. Typically in a vector approach, this is done by projection. So this is line 1, black. This is line 2, red. There is a common normal between them. So this green line segment represents that common normal. Point A on line 1, point B on line 2. The vector b minus a is a vector from a to b. That's this blue vector. You project the blue vector onto the common normal. The length of that projection is the distance between the lines. And so point, point, difference, and then the scalar projection is v dot n over the length of n, and you get 16 over root 11. Example 4, the distance from a point to a line. So let's look at a syntax-free solution. Again, one would load the Student Multivariate Calculus package. This is the point. This is the direction vector for the line. So we make the line object. We've done that before, and give it the name L. Then here's the name of the line. This is the fixed point P, whose distance from L you want to calculate. And if we go here to the Student Multivariate Calculus package, you see you have the options, one of which is find me the distance, and Maple comes back with this expression, and then you can use the approximate to float that number. Command-based solution would look like this. You would load the package using with, assignment operator, create the line object, give it the name L, or assign it to the name L. You can apply the distance command to L and the point P. I've given it the name D. Then I've applied the eval F, evaluate floating, apply that to D, and I've gotten this number. The traditional approach to these distance problems involves projection. So let's see how projection might work for us here. Here's a picture that shows the line. This green vector is the direction vector for the line. This red dot is a fixed point on the line. So those are two things you can get from the equation of the line without any trouble. This brownish color dot is the point P, and the black vector is a vector between this red dot and this brown dot. And you want to project this black vector onto the green vector. Well, it's pointing in the other direction. The green vector points in the other direction. Doesn't matter. You project down, and then you get its orthogonal component. So this is the orthogonal component. Its length is the distance of this point P from the line. It is a task template we can make use of. Task templates. Tools, tasks, browse. Table of contents, 347 task templates. The one we want is in linear algebra, visualizations, projection plot onto a one-dimensional subspace. This is the task template. It can be inserted by clicking one of these two insert buttons. Default content means you get the extra verbiage. Minimal content means you get enough to make the thing work. I've got it already embedded. You can see the path to it here. We need some data. So this is the fixed point A on the line. And I'll re-execute that. This is the direction vector V along the line. And this is the point P, whose distance from the line we want to compute. So we have these vectors defined. And what we want to project is that black vector, P minus A. And you can see here is the black vector. This gray shadow is the line. And we are projecting it onto V. Notice I've drawn V in green here. V along the line is in green here. click projection and you get the projection onto the line, but we want the orthogonal component, which is this red vector. That's this vector. Now you want to get the length of that vector. So how do you do that? Well, if you right click, you get this copy special, copy as mathml. Then you come down and you do a paste. And when you click paste, you will get this pop-up. You say yes, convert the mathml into 2D math, then you get this vector. Then you go here and you find norm, pick Euclidean. There is the length of this red vector. And then I did an approximate here. I took it to 10 digits and you get the value in floating point form. Now here is the typical vector solution done from first principles. So we define that black vector, give it the name p minus a. Right? So you write down the equation, you do over here assign name. The orthogonal component of the projection. So you project onto v, t dot v over v dot v, v. Then by subtraction, you get the orthogonal component. That gives you this vector. Let's see if we can see that here. Yeah, it's the same as this vector here. Okay? And then Euclidean norm. You saw how we found the Euclidean norm, and we did an approximation. There is an analytic solution possible for this problem. The line is a plus tv. So the points on this line are parameterized by t. This is the point p. The subtraction is a vector between a point on the line and p. So we want to find out the value of t for which this distance is minimal. So that's a vector, p minus a plus tv. So this vector, in fact, we saw how to get its norm. We do a simplify on that expression here. Simplify. It's just the square root of a quadratic. Let's give that the name f. So here's f. We do evaluate and display in lines, so it echoes back. Then here you have differentiate with respect to t, which is this. Then you hit it with a solve, and you get t equals that. And you do a substitute into. So you're substituting into, here you type the letter F. Here you type F. You get this expression, and then you do an approximate, and I've picked 5 digits, and you get the distance from P to the line. This fifth example has us find an equation of a plane containing 3 given points. A syntax-free solution to this problem. You have 3 points. Processes similar to what we did with lines. Load the Student Multivariate Calculus package. Write the 3 points as 3 lists. If you go here, you'll see lines and planes. You pick plane. That gives you the plane object. In Student Multivariate Calculus, lines and planes now gives you the option to get a representation. Representation gives you this dialog. Pick the variables, say OK. You get an equation for the plane. Now, command-based solution would have package loaded using with. The plane object is created with the plane command. Here are the 3 points. And it can wrap that with the get representation command, and the return is the equation of the plane. The traditional vector approach would look something like this. First of all, you want a picture. So you can see the pinkish thing is the plane. Down here you have the origin, and the three blue vectors are the position vectors to the points A, B, and C. By subtraction, pairwise, you get the green and the red vector. They are vectors that lie in the plane. You take their cross product, you get the normal, which is this brownish goldish color. So we need to enter the problem data, the points A, B, C, use assign name, generic position vector, same thing, pairwise subtractions. I call them AB for B minus A, AC for C minus A. The normal is the cross product. I've shown in an earlier example how to get a cross product. Then the vector equation for the plane is R, which is x, y, z, minus one of the points on the plane, R minus A. That has to lie in the plane. So to make it lie in the plane, you make it orthogonal to the normal. So that dot n equals 0, and that returns the equation. Now there's a purely algebraic solution to this problem, and I'd like to show it because it contains a piece of maple wizardry that would be otherwise hard to find. The very first thing I want to do is I'm going to define equations of planes as a scalar valued function of a vector argument. I want the argument of this function f to be a vector, not a bunch of components, but I want it to be a vector. And the way you do it is you use the name, for example, v, for the name of the vector, and then wherever you want x, y, z to show up, you use the components of the vector, and this is v1, v2, v3, and these are table entries. They're not atomic variables. These are table entries. So f equals 0 would give you the equation of a plane. So we use over here, after we type this thing out or copy and paste it, we use assign function. Okay, so that defines the appropriate function. Now, A, B, and C have to satisfy the equation of this plane. So f at A is 0, f at B is 0, f at C is 0. These are three equations. There are four unknowns, but really there are only three things to calculate because one of those parameters, A, B, C, or D, has to be non-zero. If you divide through by that parameter, then you really have only three things to obtain. So you click here, you pick solve, and you solve. Let's show you what you here. Solve for variables. Okay, pop up lets you place in here A comma B comma C. So you're solving for A, B, C in terms of D. That's this. Then you use a substitute into, and you substitute into f of r. And you put f of r equals 0, so much the better. So this is the return of that substitute into, and you'll notice there's a d in each term. The simplest way to get rid of that d is to give it a value that's nice, like negative 86. So here, evaluate at a point and give d the value of negative 86, and you get the equation of the plane. So this answer differs from this answer from a minus sign multiplied through. Example 6. Equation of a plane through a point, and you have its normal. So there's a task template, and I've showed where the task templates are, and here's the path to it. Linear algebra, visualization, plane plot. Variables, x, y, z. Normal, here's the normal. Point given as a vector. Okay, you can see there's the point, 5 minus 3, 7. Normal, you can read it off here. 3 minus 5, 2. the number of digits that are going to be displayed, because this is an interface to the plain plot command. If you click this button, it executes the data in this command, the plain plot command, and what you get is echo back of the normal, or we knew that. You get the equation of the plane, but notice it's all in floating point coefficients. The nearest point on the plane near the point on the plane nearest the origin, and two basis vectors. And you can see here in the figure that's drawn, you get a picture of the plane that's gray. Down here is the origin. This bluish color vector is from the origin to the point on the plane closest to the origin. This red vector is from the origin to the point on the plane P, given point. The two basis vectors are drawn here, and the normal to the plane is drawn here. Now, a syntax-free solution using the lines and planes tools. Load the package, point, normal, plane object, representation. So we've done this several times. No surprises there. A command-based solution uses the with command, the plane command. Here's the point, here's the normal. I've used the assignment operator to give that the name Q. Then I apply get representation to Q. I get this equation. And here's a case where you can draw a picture. So you apply get plot to this plane Q, and you get a picture of the piece of the plane, point, and the normal. The traditional vector solution can be implemented this way. Student multivariate calculus package. The data, you need the point P, you need the normal, and the generic position vector. These are all position vectors, and it's done as we've seen before with the assign name option in the context panel. Then the vector equation of the plane is the generic vector R minus fixed point P. That has to be orthogonal, or it has to lie in the plane, so it has to be orthogonal to N, and you get the equation of the plane. Now you might want to compare, can we close this? Compare that to what we have here, 3x minus 5y plus 2z minus 44. Bring the 44 over. So these solutions agree. Example 7. We want to find the equation of a plane that contains 2 points and a direction. So the difference here, you get a vector in the plane, vector, vector, cross product, get a normal. So this information determines the plane. So let's see the syntax-free approach. So load the student multivariate calculus package. This is the vector. Here are the 2 points. That's enough information to make a plane. So make plane and get its representation. Command-based solution would run like this. With, to get the student package in, the plane command applied to the vector and the 2 points. That's enough information to determine the plane. So you got a plane object. Apply the get representation command to the plane object, get the equation of the plane. And here, because you're using commands, you can use the get plot command, and you get the plane and the normal to the plane. The traditional vector solution to this problem. Well, we need a picture. So you can see here the plane, the two blue vectors coming out of the origin are the position vectors to the 2 points that are given. By subtraction, you get this black vector. The red vector is the direction that was given. Cross product gives you the normal, which is the green vector. And now you have enough information to construct the plane. The implementation of what's in that picture goes like this. Well, we need the Student Multivariate Calculus package. We need some vectors defined. So here are the 2 points defined as position vectors. This is the direction vector, and this is the generic vector to an arbitrary point in R3. This is the difference from P to Q. Okay, that's the black vector here. Cross product gives you the normal, and then the equation of the plane as vectorially r minus a point. This vector has to lie in the plane, force it to lie in the plane, you make it orthogonal to the normal, so dot product equals 0, gives you the equation of the plane. There's an algebraic solution to this problem, and it uses the device that we saw earlier, but in a slightly different form. So what is it that we don't know? We don't know the normal to the plane. So let's let n be this generic vector, ABC. Okay, so make that assignment. Then we define this scalar valued function of the vector argument v. So what is that function? N dot xyz. But you don't use xyz. You have to use v1, v2, v3 as table elements. And v is the name of the table. You cannot use atomic variables here. These have to be table elements. So in that vector plus d, that's the equation of a plane if you put the right numbers in. So there are 3 conditions that you can impose. This normal n must be orthogonal to the given direction v. So n dot v equals 0. And then the 2 points p and q have to be have to satisfy the equation of the plane. So f of p 0, f of q 0. That gives you 3 equations. There are 4 unknowns, but remember, there are really only 3 unknowns because at least one of these coefficients ABC has to be 0. ABCD has to be non-zero. You can divide by it. So you really have 3 things to compute. So you solve, you get this answer back. You substitute into f of r. And you can even set that equal to 0. Then you have the equation of a plane. Pick a reasonable value of d so it makes things simplify. So take it to be negative 12, and you get 5x 2y minus 12 minus z equals 0. Now you'll notice that up here, the equation that you got vectorially has every coefficient multiplied by 2. So here it comes out to be slightly simpler. This vector approach, you have an extra factor of 2. I think we have time to do example 9. So I'm going to skip 8. I'm going to do example 9. So in example 9, we are asked to find the equation for a plane that contains the line of intersection of these 2 planes. So it's a hidden way of giving you a line. So you have a plane that contains this line and this point. syntax-free solution. So we've seen all of these steps before. Student multivariate calculus package define the two given planes. So I'll call those Q1 and Q2. We've seen how to define those planes. Now, I want the line of intersection of those two planes. So you write the names Q1, Q2. You do an evaluate display in line, command control equal. So you have the two plane objects from which you can get the intersection. But that intersection is itself a line, and I give that line the name L. Now I want the plane that contains the given point, so that's the list, and the line L. So make plane. There's the plane object. Now I'm going to give it the name Q3 because I want to do some stuff with it. So the first thing I want to do with it is to get the equation of the plane. So I write the name Q3, do an evaluate and display in line. So I have the plane object. Then I get its representation. So there's the equation of the plane. And then I just thought I would verify that the plane, the given plane, contains the appropriate items. So here I check that the plane contains the given point. So there's the name of the plane, there's the point, you do an evaluate and display in line, you get an echo back of the plane object and the point. So look here in the context panel, lines and planes contains, and the echo is true. Yes, so the plane Q3 contains the point. And then you do the same thing here. You have the name of the plane, name of the line, evaluate and display in line, and then you query contains. Does the plane contain that line? Echo back true. The command-based solution would run like this. For the package, assign to the Q1 and Q2 these planes using the plane command. Get intersection. That will give you the line of intersection. Then the plane that contains that line and the given point, use the plane command and the get representation command to get the equation of the plane. To do the verifications, you can use the contains command. So basically you read it as, does Q3 contain this point? True. Does Q3 contain this line? True. To verify that the plane contains point, using first principles, you would use the eval command. So you evaluate the plane, this equation, using x equals 2, y equals minus 3 is equals 1. You get 14 equals 14. To show that the appropriate direction is in the plane, you get the normal to the plane, you get the direction of L. They have to be orthogonal, so you take the dot product and you get 0. For a vector solution, we first draw a picture. These two pinkish or reddish looking planes are the two given planes. Green plane is the solution plane. I've drawn that in place. If you take the cross product of the normals of the two given planes, you will get the vector v, which is this black vector along the line of intersection. You need a point A on that line, so you could take uv0, where u and v are two numbers to determine. Vector w is this goal vector, p minus a. Cross product gives you this red vector, the normal to the green plane, you would get what you need. Okay, implementing these ideas for the vector solution. Define the two normals for the given planes. Take the cross product, get the vector v, that's that black vector in the line. We want to find this point A, uv0. So you evaluate these two planes at z equals 0. You have two equations for x and y, which you solve and you get an x-y pair. Substitute that back into the vector x, y, 0. You get this vector, which we will call A, so it's a position vector to the point A. Then you need a generic position vector. You need the point P as a position vector. You need the difference, that's W. And the cross product, that's N3. Once you have that information, then the vector equation of a plane r minus p dot the normal equals 0. Now, the result that you get is, can be simplified by taking out a factor of 10. If you compare this, well, what can we compare it to? Up here, 8, 3, 11, 14, 8, 3, 11, 14, if you take out that factor of 10. There is an algebraic solution to this problem. Here are things that we already know. A, P, and R. Right? R is a generic vector. A is a point on the line of intersection. P is a point that has to lie in the plane. Okay, let's get another point on the line of intersection. Let's get a point where z equals 1, because A is the point where z equals 0. So here are the two planes. We evaluate them at z equals 1. You get these two equations, which you solve. Substitute into the vector x, y, 1. You get this vector, which we will call B. So it's a second point on the line of intersection. We use this same trick here that we've used before. Define a scalar valued function of the vector argument v. That will give us the equation of the plane. And there are 3 points that have to lie in this plane. A, B, they have to be on the line of intersection, and P. So you have 3 points that have to be on the plane. So this problem we've already solved. You need 3 equations. F of A equals 0, F of B equals 0, F of P equals 0. Here are the equations. Solve them for A, B, and C as a function of D. Substitute that back into f of r equals 0, and then choose a nice value for D. I chose negative 14. Yes. And we have this reduced equation, 8, 3, 11, 14.